Today we shall study about atoms in modern physics. The first model of atom was proposed by J.J. Thomson in 1898. According to this model, the positive charge of the atom is uniformly distributed throughout the volume of the atom and the negatively charged electrons are embedded in it like seeds in a watermelon. This model was called plum pudding model of the atom. We know that condensed matter, solid and liquids, and dense gases at all temperatures emit electromagnetic radiation in which a continuous distribution of several wavelengths is present, though with different intensities. This radiation is considered to be due to oscillations of atoms and molecules governed by the interaction of each atom or molecule with its neighbors. In contrast, light emitted from rarefied gases heated in a flame or excited electrically in a glow tube, such as the familiar neon sign or mercury vapor light, has only certain discrete wavelengths. The spectrum appears as a series of bright lines in such gases. The average spacing between atoms is large, hence the radiation emitted can be considered due to individual atoms rather than because of interactions between atoms or molecules. Rutherford proposed the planetary model of the atom, was also called nuclear model of the atom. According to this, the entire positive charge and most of the mass of the atom is concentrated in a small volume called the nucleus, with electrons revolving around the nucleus just as planets revolve around the sun. But it could not explain why atoms emit light of only discrete wavelength. How could an atom as simple as hydrogen, consisting of a single electron and a single proton, emit a complex spectrum of specific wavelengths? In the classical picture of an atom, the electron revolves around the nucleus much like the way a planet revolves around the sun. So there are some serious difficulties in accepting such a model. Alpha particle scattering and Rutherford's nuclear model of atom. In 1911, H. Geiger and E. Marsden performed some experiments. In one of their experiments, as shown in Figure 1, they depicted a beam of 5.5 mega electron volt alpha particles emitted from bismuth 83 to 240, radioactive source at a thin metal foil made of gold. The Figure 1 and 2 show the scattering experiment and the schematic diagram of H. Geiger and Marsden experiment. Now Figure 1 shows a schematic diagram of the experiment. Alpha particles emitted by bismuth 83 to 214 radioactive source were collimated into a narrow beam by their passage through lead bricks. The beam will be allowed to fall on a thin foil of gold of thickness 2.1 × 10 to the power minus 7 meter. The scattered alpha particles were observed through a rotatable detector consisting of zinc sulfide screen and a microscope. The scattered alpha particles on striking the screen produced brief light flashes or scintillations. These flashes may be viewed through a microscope, and the distribution of the number of scattered particles may be studied as a function of angle of scattering. Figure A shows the data point of the experiment. A typical graph of the total number of the total number of alpha particles scattered at different angles in a given interval of time, the interval of time, then in figure A, that dots in the figure represent the data points, and the solid curve is the theoretical prediction based on the assumption that the target atom has a small, dense, positively charged nucleus. Many of the alpha particles pass through the coil. It means that they do not suffer any collisions. Only about 0.4% of the incident alpha particles scatter by more than 1 degree, and about 1 in 8,000 deflect by more than 90 degrees. Rutherford argued that to deflect the alpha particle backwards, it must experience a large repulsive force. This force could be provided if greater part of the mass of the atom and its positive charge were concentrated tightly at its center. Then the incoming alpha particle could get very close to the positive charge without penetrating it, and such a close encounter would result in a large deflection. This agreement supported the hypothesis of the nuclear atom. This is why Rutherford is credited with the discovery of the nucleus. In Rutherford's nuclear model of the atom, the entire positive charge and most of the mass of the atom are concentrated in the nucleus, with the electrons some distance away. The electrons would be moving in orbits about the nucleus just as the planets do around the sun. Rutherford's experiment suggested just as the planets do around the sun. Rutherford's experiment suggested the size of the nucleus to be about 10 to the power minus 15 meter to 10 to the power minus 14 meter. From kinetic theory, the size of an atom was known to be 10 to the power minus 11 meter, about 10,000 to 1 lakh times larger than the size of the nucleus. Thus, the electron would seem to be at a distance from the nucleus of about 10,000 to 1 lakh times the size of the nucleus itself. Thus, most of an atom is empty spaces. With the atom being largely empty space, it is easy to see why most alpha particles go right through a thin metal foil. However, when an alpha particle happens to come near a nucleus, the intense electric field there scatters it through a large angle. The atomic electrons, being so light, do not appreciably affect the alpha particles. Figure A shows the scattering data, so computation of the trajectory of an alpha particle scattered by a single nucleus is enough. Alpha particles are nuclei of the helium atom and carry 2 units, 2e of positive charge, and have the mass of the helium atom. The charge of the gold nucleus is Zi, where Zi is the atomic number of the atom. The gold Z barabar 79. Thus, the nucleus of the gold is about 50 times heavier than an alpha particle. It is reasonable to assume that it remains stationary throughout the scattering process. Under these assumptions, the trajectory of an alpha particle can be computed implying Newton's second law of motion and the Coulomb's law of electrostatic force of repulsion between the alpha particle and the positively charged nucleus. The magnitude of the force is F barabar 1/4 pi epsilon naught 2E into Z bata R square, where R is the distance between the alpha particle and the nucleus. Now the alpha particle trajectory, as shown in the figure, the trajectory traced by alpha particle depends on the impact parameter B of the collision. The impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. In case of head-on collision, the impact parameter is minimum, and the alpha particle rebounds back. For a large impact parameter, the alpha particle goes nearly undeviated and has a small deflection. क्या होगी